In problem 1, we will compute these four limits using the piecewise function f of x. We'll then use these limits to determine if the function is continuous at -1 and +3. Let's start with this limit here. That is the limit as x approaches -1 from the left of f of x. If we are to the left of -1, we're talking about this portion of the definition. I'm going to use 7 minus x squared in place of f of x. So this is the limit as x approaches -1 from the left of 7 minus x squared. As 7 minus x squared itself is continuous, we can put -1 in place of x here to solve the limit. This is equal to 7 minus -1 squared. So that's really 7 minus 1, which is 6. This is the value as we approach -1 from the left of the function f of x. If we compare this to the limit as x approaches -1 from the right of the function f of x, this is equal to the limit as x approaches -1 from the right of. If we're approaching -1 from the right side, we'll use minus 4x plus 2 for the function. As minus 4x plus 2 is itself continuous, again, we can put -1 in place of this x. So this is minus 4 times -1 plus 2. That is 4 plus 2, which is positive 6. So what does this mean? As we approach -1 from both the left and the right side, we get that the limit is equal to 6. This means the limit as x approaches -1 overall of the function f of x exists, it's equal to 6. That's also equal to the value of the function at -1. This means f is continuous at x is equal to -1. We'll do the same argument, but now we'll check 3 instead of -1. So for that one, I'll put my work over here. What is the limit as x approaches 3 from the left of the function f of x? If you approach 3 from the left, we're again going to use minus 4x plus 2. As minus 4x plus 2 itself is continuous, we can simply put 3 in place of x. And when we simplify this, this is -12 plus 2, that's -10. So here we approached 3 from the left using this portion of the piecewise function, and we got -10 as our limit. I'm going to open up a new slide and do a similar computation, but as we approach 3 from the right. The limit as x approaches 3 from the right of the function f of x, if you look back at the way the equation is defined, if we're to the right of 3, f was defined to be x squared plus 1. X squared plus 1 itself is continuous, so we can put 3 in place of x. We get 3 squared is 9 plus 1 is 10. I'm going to note that the limit as x approaches 3 from the left of f of x was -10, and that is not equal to the limit as x approaches 3 from the right of the same function because it was equal to +10. This means the limit as x approaches 3 overall does not exist. Therefore, f is not continuous at x is equal to 3. So not continuous here, but it was continuous at -1. In problem 2, we're going to use the limit definition of the derivative to find f prime of x, where f of x is this function here. So part of this problem is actually recalling the definition for the derivative. That is the limit as h goes to 0 of f of x plus h minus f of x all over h. If we plug this information into the function f of x, in place of every single x, I'll put an x plus h. I'll then subtract the function using parentheses and simplify this fraction, hopefully canceling the h from the denominator. This is the limit as h goes to 0 of, okay, we have 5 minus, in place of this x, I'll put an x plus h. Then I'll subtract 2 times x plus h squared. We now subtract f of x itself. So I'll put the subtraction symbol. The function f of x is 5 minus x minus 2x squared. But be careful. You have to use parentheses. You're subtracting the entire function. This is all divided by h. This is the limit as h goes to 0. I'm going to start multiplying and expanding and canceling terms. So I have 5. That's really minus x minus h. If you square x plus h, maybe I'll put this up here kind of like off to the side. X plus h squared is equal to x squared plus 2xh plus h squared. I can now distribute a negative 2 to this thing. That really gives me minus 2x squared minus 4xh minus 2h squared. I'll now distribute the negative into the parentheses next. We get minus 5 plus x plus 2x squared. This whole thing is divided by h. Let's cancel as much stuff as we can. I see there's this plus and minus x. Those cancel. We have a positive and negative 5. Those cancel. And positive 2x squared and a negative 2x squared. And that is it. There's nothing else that cancels, so I'm going to write down this is equal to the limit as h goes to 0 of, we have minus h minus 4xh minus 2h squared all divided by h. And we can cancel an h from every single term. By that I mean if you divide everything by h, that becomes 1. This becomes negative 1. This is gone. And that exponent drops down by 1. This whole thing is equal to the limit as h goes to 0 of, the denominator is 1. I'm not going to write it. We're left with minus 1, minus 4x, minus 2h. If you put 0 in place of h, you get minus 1 minus 4x. This is what f prime of x should be equal to. And if you'd like, you can use your shortcut derivative rules to verify this. The derivative of 5 is 0. Minus x goes to minus 1. Bringing down the 2, we get minus 4x. So I'm confident that this is correct. In problem 3, we'll use L'Hopital's rule to solve 3 separate limits. If you look at this very first limit, you should ask, what happens if I put 0 in place of all of the x's? If you do this, you get e to the 0 minus 1 all over 0 squared plus 0. That's 1 minus 1 over 0. Hey, this is a 0 over 0, an indeterminate form, meaning L'Hopital's rule does in fact apply. This should be equal to the limit as x goes to 0 of, I'll take the derivative of the top and the bottom. The derivative of the numerator is e to the x, and for the denominator, you get 2x plus 1. Okay, if this limit exists, by L'Hopital's rule, it'll be equal to this limit. If you look at this limit, can you just simply put 0 in place of x to get your answer? Yeah. If you substitute 0 in place of x, you get e to the 0 divided by 2 times 0 plus 1. E to the 0 is 1. The denominator is 1. In fact, this limit is equal to 1. In part B, we're going to use L'Hopital's rule again to solve this limit. I'm going to first check by putting 0 in place of all the x's. This is equal to 2 times sine of 0 minus sine of, well, 2 times 0 is still 0, all divided by 0 minus sine of 0. Sine of 0 itself is equal to 0, so this whole thing is actually 0 over 0. Therefore, we can apply L'Hopital's rule. I'll take the derivative of the top and the bottom separately in this fraction, and if this limit exists, it should be equal to this one. If you take the derivative of the top, let's see, the derivative of 2 sine x is 2 cosine x, and then you have minus, the derivative of sine goes to cosine, it'll still be of 2x, but by the chain rule, you have to multiply by 2. The derivative of the denominator is 1 minus cosine x. So if you can take 0 and put it in place of all the x's and get a number, it'll be equal to this limit. So let's see what happens if we put 0 in place of x this time. This is 2 cosine of 0 minus, that's really 2 times, again, cosine of 0. I just put the 2 first. Divided by 1 minus cosine of 0. What does this whole thing simplify to? Cosine of 0 is 1. This means the top is 2 minus 2 over 1 minus 1. We again have a 0 over 0. This means we can actually apply L'Hopital's rule again. If the new limit we get exists, it'll be equal to this one, which will be equal to this one. I'm going to rewrite this by putting the 2 first. This isn't essential, but I like to rewrite it. We have the limit as x goes to 0 of 2 cosine x minus 2 cosine 2x. That's all divided by 1 minus cosine x. I'll now apply L'Hopital's rule. For the derivative of the top, okay, cosine goes to negative sine. Therefore, the first one is minus 2 sine x. Again, cosine goes to negative sine. So we'll have a negative sign making this positive. So it's going to be positive. I'll leave that 2 alone for a second. It's going to be positive sine of 2x. Now there's a 2 here that travels along, but at the same time, if you take the derivative of 2x by the chain rule, a 2 would multiply out. Since I have a 2 here and a 2 here, I'll instead put a 4 first. The derivative of minus 2 cosine 2x is positive 4 sine 2x. And the denominator is the derivative of 1 goes to 0. Cosine goes to negative sine. We'll again have an extra negative to make it positive sine. If this limit exists, it'll be equal to all of these, meaning we've found this limit. Does this exist? Again, we get another 0 over 0. If you look at this, this is minus 2 sine of 0 plus 4 sine of 0 all over sine of 0. That is 0 over 0. Okay, I think maybe this will be the last time. I'll apply L'Hopital's rule one more time, and if that limit exists, it'll be equal to all of these, including the one that we started with. So using L'Hopital's rule again, this is the limit as x goes to 0 of, okay, we have minus 2 cosine x. That'll be plus 8 cosine 2x. So why did it go to cosine? The derivative of sine is cosine. It was originally a 4, but by the chain rule, since another 2 came out, 4 times 2 gave me 8. And in the denominator, we have cosine of x. Can we now simply put 0 in place of all the x's to get our answer? We can. Cosine of 0 is 1. So if we substitute in 0, this is minus 2 cosine of 0 plus 8 cosine of 0 all over cosine of 0. Because cosine of 0 is 1, this is really negative 2 plus 8, which is 6. 6 divided by 1 is still 6. And this is the answer to part B. We had to use L'Hopital's rule 3 times. In part C, we're looking at the limit as x goes to infinity of 1 minus 2 over x to the power of x. I'm going to note that as x goes to infinity, this is of the form 1 to the power of infinity, which is an indeterminate form. This means when we rewrite the expression, every limit we have will be an indeterminate form. This means L'Hopital's rule will apply. I'm going to do a trick for this problem. If this limit exists, I'll call it L. Therefore, the natural log of this limit should be equal to the limit as x goes to infinity of the natural log of 1 minus 2 over x to the power of x. The reason introducing a logarithm like this is nice is because we have a property that says we can bring this x down front. This is equal to the limit as x goes to infinity of x times the natural log of 1 minus 2 over x. To apply L'Hopital's rule, we have to write this thing as a fraction. This exponent is a positive 1. I'll put it into a denominator by making it a negative 1. This is the limit as x goes to infinity of, so it's really in the denominator x to the negative 1. The top is the natural log of 1 minus, you know what? Actually, with this exponent of 1, I'll bring it up to the top and make it 2x to the negative 1. it'll be easier to take the derivative this way when we apply L'Hopital's rule. So this is equal to this. Again, the reason was I wanted a fraction, so I made this exponent -1, and it went down here. This is a fraction, and currently this is a positive one here, but if you bring this up to the top, you'd make its exponent -1 as well. If we apply L'Hopital's rule, we will take the derivative of the top and bottom of this fraction. I'll start with the denominator. You get -x to the -2. For the natural log, you get 1 over this thing, so you have 1 over 1 minus 2x to the -1. But by the chain rule, you have to take the derivative of 1 minus 2x to the -1. This goes to 0. This will become positive 2x to the -2. To solve this limit, I'm going to simplify the fraction a little bit. For starters, the x to the -2 cancels with just the x to the -2. Notice that this number 2 is left over, and so is this -1. You can take this negative and actually factor it out of the limit. You can do the same thing with this number 2. In fact, I'm going to factor both of those out. This is equal to -2 times the limit as x goes to infinity of. This denominator is now equal to 1, so you don't really need to write this divided by 1. In fact, I'll only write this fraction. 1 divided by 1 minus 2x to the -1. And for me, I like to think of this as a fraction. I'll put this back as 2 over x. I'm writing it this way because as x goes to infinity, this goes to 0. So this whole limit is 1 divided by 1 minus 0. So I'll put that over here. That's -2 times 1 divided by 1 minus 0. This equals -2 overall. Now this is not the final answer. This -2, it's not equal to the limit. It's equal to the natural log of the limit. So I'll just put that here like this. Because -2 is equal to the natural log of L, you can exponentiate both sides. This side is just L, and this side is e to the -2. This gives us our answer. The limit is equal to e to the -2. This last step is really important, but this is the final answer. In problem 4, we'd like to find the antiderivative of the function f of x, which is expressed here. But we'd like to find the particular one that satisfies f evaluated at 0 is equal to 15. So to start with, if you find an antiderivative, that means if you take its derivative, it should be equal to f of x. So I'll start by finding the most general antiderivative. Here I'll start with this 5 sine of x. The antiderivative of sine is negative cosine. So this is minus 5 cosine of x. We then have minus 2. Okay, secant squared. I know the derivative of tangent is secant squared, so I should have minus 2 tangent x. All right, then we have minus e to the x. Well, e to the x is its own derivative, and therefore it is its own antiderivative. 10 would come from 10x because the derivative of 10x is 10. And I'll also add this arbitrary constant. So this thing is the most general antiderivative of this. But we'd like to figure out what number c will make this a true statement. So in this general antiderivative, what I'll do is put 15 in place of f of x, provided that I put a 0 in place of all of the x's. If you go through, we'll have 15 is equal to cosine of 0 is -1, so that's equal to -5. Tangent of 0 is 0, so 0 times -2 is 0. I won't even write that portion. Then we have minus e to the 0. E to the 0 is 1, so I get minus 1. 10 times 0 is 0. I'm not going to write that. And then we have plus c. So we have that 15 is equal to minus 6 plus c. If you add 6 to both sides, you get 21 is equal to c. What does this mean altogether? it means that the answer we're looking for is capital F of x is equal to minus 5 cosine of x minus 2 tangent of x, that's minus 2, minus e to the x plus 10x, and then plus 21. It is that constant that will give us the antiderivative that we're looking for. In problem 5, we're given the function f of x, its derivative, and second derivative. Using this information, I'd like to find the intervals on which the original function is increasing and decreasing, where the original function is concave up and concave down, and then find any local mins, maxes, or inflection points. So to start with, for increasing and decreasing, I'm going to use the derivative itself. I'm going to check to see where the first derivative is equal to 0. And from that, I'm going to figure out where it is positive and negative. So for the first derivative, that is 2x e to the 2x plus e to the 2x. So we don't actually have to take the derivative. It's given to us in this problem. Where is this thing equal to 0? I'm going to factor this. You can factor out an e to the 2x. And what is left over is 2x and plus 1. This thing is equal to 0 wherever 2x plus 1 is 0. This is always positive. And 2x plus 1 equals 0 if x is equal to negative 1/2, because you would subtract 1 and divide by 2. On a number line, I'm going to express what the first derivative is doing. It is equal to 0 at negative 1/2. Because this is always positive, your derivative is going to be positive or negative depending on whether 2x plus 1 is positive or negative. This is an increasing linear function. It would go through negative 1/2 like this. This means it's positive on the right and negative on the left. So I'll note that over here it's positive and over here it's negative. This tells us everything we need to know about local mins, maxes, as well as increasing and decreasing. So where is f increasing? That's where the first derivative is positive, and therefore that's on the interval from negative 1/2 to infinity. Where is f decreasing? That's where the first derivative is negative, so that's from negative infinity to negative 1/2. Note that we have a local min at x is equal to 1/2. So we have a local min at x is equal to negative 1/2. And this is because the derivative goes from negative to positive. Your original function must be decreasing and then increasing, so it has to be a lowest point on the function. For concave up, concave down, and inflection points, we'll do almost an identical process, but not for the first derivative. We'll instead use the second derivative. I'll put this on a new slide. So here's the second derivative, and I set it equal to 0. If you'd like to solve this thing for x, I can again factor out an e to the 2x, but also a 4. And if we do this, we get 4 e to the 2x, and what is left over is x plus 1. This part here is never 0. In fact, it's always positive. So I can figure out where this is 0 by setting this equal to 0. So where is x plus 1 equals 0? That is if x is equal to negative 1. This is a potential location for an inflection point. On a number line, I'm going to draw where the second derivative is 0 and then label it as either positive or negative around this value. So here is where the second derivative is 0. Again, this is a linear function with a positive slope. Therefore, it is increasing through this point. This is always positive, so we can use this to figure out where the second derivative is positive or negative. It is positive to the right. It is negative to the left. So where is f concave up? Well, that's when the second derivative is positive, which is on the interval from negative 1 to infinity. Where is f concave down? Well, that's where the second derivative is negative, which is from negative infinity to negative 1. The last thing I'll note that there is an inflection point. on the function f at x is equal to -1. And this is because there is a change in concavity. That is, I see the original function goes from concave down to concave up. In problem 6, we're told that a particle moves in a straight line with this acceleration, -2t plus 8 centimeters per second squared. We know its initial displacement is s of 0 is equal to 1 centimeter, and this is the initial velocity, 4 centimeters per second. I'd like to find a formula for the function s of t. So to start with, if you know a of t, whatever function it is equal to, if you want to find v of t, it is the function whose derivative is equal to a of t. So this means that v of t is the antiderivative of -2t plus 8. That is -t squared plus 8t plus some constant c. You can check that this is true by taking the derivative of this function, which will give you this. Now here I have an arbitrary constant, but I think we can use this piece of information here to figure out what c should be equal to. That is, if you put 0 in place of t, the output should be v at 0. That is, 4 is equal to -0 squared plus 8 times 0 plus c. I can see that this is 4 is equal to c. Therefore, v of t is equal to minus 2t squared plus 8t plus 4. That makes sense. If you put 0 in place of these two values of t, 4 is going to be the value that makes this a true statement. Now, if you'd like to find s of t, the displacement, I'll note that this is the function s, whose derivative is equal to v. Therefore, I'm again going to find the antiderivative, but of the velocity function this time. The antiderivative of -t squared is minus t cubed over 3. For 8t, that's going to be 4t squared. For 4, that's going to be 4t. And then we'll have another constant, I'll call it d instead of c, because it will possibly be different than this one here that we called for. To figure out the value of d, I'll use this other piece of information. So by using this here, I should be able to solve for this. I'll put 1 in place of s of t and 0 in place of all these values of t. This will simplify nicely. 1 is equal to -0 cubed over 3 plus 4 times 0 squared plus 4 times 0 plus d. This all simplifies really quickly to 1 is equal to d. Therefore, what I'll do is, in this formula, I'll rewrite it, but put a 1 here instead of the letter d. I'll put that on the next slide. We have that s of t is equal to, that was -t cubed over 3 plus 4t squared plus 4t plus 1. This will tell us the displacement of the particle at any given time t. In problem 7, I'd like to use the methods of calculus to find the point on the line y is equal to 8 minus 2x that is closest to the point 1, 1. And here we can use the distance formula if we need to figure this out. Graphically, what we are doing is, if you look at the linear function 8 minus 2x, so that's something like this. Here's y is equal to 8 minus 2x. And here's the point 1, 1. There has to be some point on this function right there that is closest to 1, 1. And the question is, where are the coordinates of that point? And that's what we're trying to find. What we can do is use the distance formula to get an equation between any point and the point 1, 1, and then take the derivative of this thing and set it equal to 0 to find the actual closest point. To apply this formula, we need two different points, and they're over here. One I'll call xy, and the other I'll call 1, 1. So just being a little more careful, x2, y2, from the formula, I'll call that xy. That means x1, y1 from the formula should be the other point, which is 1, 1. So the distance d, it's the square root of, that's really x minus 1 squared plus y minus 1 squared. Okay. To take the derivative of this formula, it should be either x's or y's, and here I have two separate variables. Since y is equal to 8 minus 2x, I can replace this with 8 minus 2x. And furthermore, if you'd like to take the derivative of this formula to minimize it, you can actually just minimize what is underneath the square root itself. So what I'm going to do is I'm going to call this a different function. I'm going to call this f of x, and I'm going to let it equal the thing that is underneath the square root, which is x minus 1 squared plus, I think I'll call this, since I have 8 minus 1, I'll call it 7 minus 2x. So what I'm going to do is minimize the thing under the square root. That is good enough to minimize the distance overall. To minimize this function, I'm going to take the derivative and set it equal to 0 and solve for x. So f prime of x is equal to, okay, I'll bring down the 2, copy down the x minus 1, subtract 1 from the exponent. By the chain rule, you have to multiply by the derivative of the inside, which is 1. I won't write the exponent of 1, and I won't write times 1 either. I'll instead move on to this next piece. I'll bring down the 2, so that's plus 2 times 7 minus 2x. The exponent is now going to be not 2 but 1. And by the chain rule, you have to multiply by the derivative of the inside, which is negative 2. So here is the derivative. Before I set this equal to 0 and solve for x, which will definitely tell us the minimum distance that we're looking for, I'm going to simplify this function by multiplying this negative 2 here, and then start distributing things in and collecting like terms. I'll do this on the next slide. So here's my function f prime of x. F prime of x is equal to, if you distribute in the 2, we get 2x minus 2, plus, if I take this 2 and multiply it to this negative 2, that's negative 4, which I can put right here. So in fact, I'm going to get rid of that and call it minus 4 times 7 minus 2x. I can now multiply negative 4 into the parentheses. So we get 2x minus 2 minus 28 plus 8x. All right, so f prime of x is equal to, we have a 8x and a 2x, which is 10x. We have a minus 2 and a minus 28, which is minus 30. And I like to take the derivative and set it equal to 0 to solve for x. This is where 10x minus 30 is equal to 0. That's where 10x is equal to 30. And therefore, x is equal to 3. That must be the x value of the point on the graph 8 minus 2x that's closest to the point 1, 1. We need to find what y is equal to, but y was equal to 8 minus 2x. If you put 3 in place of x, you get 8 minus 2 times 3. That's 8 minus 6, which is 2. So what's the coordinate on the line 8 minus 2x closest to the point 1, 1? The x coordinate is 3, and the y coordinate is 2. So this is the answer for this problem. Let g of x equal 2x squared plus 2. In part A, it asks us to use a left endpoint Riemann sum with n is equal to 4 rectangles to estimate the area bounded by the function g of x, again, which is 2x squared plus 2, and the x-axis on the interval from 0 to 4. Instead of overcomplicating this by drawing an exact picture of 2x squared plus 2, I'm going to draw a number line. So here is 0, and here is 4. That is this interval. We'd like to divide it into 4 rectangles. And there's a very easy way to do this. You can count by 1. So 1, 2, 3, 4. That's 1, 2, 3, 4 rectangles. Using our formulas, the base length of each rectangle should be 1. That's going to be equal to the length of the interval divided by the number of rectangles that you want, and certainly you get 1 for each of those. You want to find the area of the rectangle where this is a base and the g of x function is telling you the height. So we'll use the left endpoints of each interval to determine the height of each rectangle, and the base of each rectangle is going to be equal to 1. This question is asking us to find L sub 4. So 4 rectangles using left endpoints. Each one's going to be the base length of the rectangle times the height of the function at the left endpoint. So the first one will be delta x times g of 0. Then we have delta x times g of 1 plus delta x times g of 2. And the last one is delta x times g of 3. So that's going to be 1 times, all right, g of 0 is simply 2, so we get 1 times 2, plus 1 times, all right, g of 1 is 1 squared is 1, 2, and then we have 2 plus 2, which is 4. Next, we want g of 2. It'll be 1 times g of 2, so it's going to be 1 times, okay, if you square 2, you get 4. 4 times 2 is 8, plus 2 is 10. Our last one is going to be here at 3. If you square 3, you get 9. 9 and 2 is 18, and 2 more is 20. So this sum is equal to, that's really 2 plus 4 plus 10 plus 20. So that's 20, 30, 34, 36. This is the estimate that we're looking for using left endpoint Riemann sums. For part B, we now would like to find the exact area under the curve of 2x squared plus 2 between the endpoints of 0 and 4. And we're going to do this using the limit definition of the integral and potentially these sum formulas as well. So to start with, I'm going to list out a few things. What is delta x equal to? In this case, it's going to be the difference of the endpoints divided by some number of rectangles, and that I'll just call n. So this is equal to 4 over n. That is the base length of each rectangle if you have n rectangles. The other thing that we're going to need is, well, what are the endpoints that we're using? We call those things x sub I. That is where you start, which in this case is 0, plus I times the base length of each rectangle. So x sub I is equal to 4 over n. Once you have established these two things, by definition, the definite integral from 0 to 4 of the function 2x squared plus 2 dx, that is equal to the limit as n goes to infinity of the sum of I going from 1 to n of f of x sub I times delta x. We will compute this sum, and then we'll figure out the limit of what is left over. So to get f of x sub I will take x sub I and put it in place of this x. Delta x is equal to, in this case, 4 over n, and I'll multiply by that next. So this is the limit as n goes to infinity of the sum of I going from 1 to n. F of x sub I is 2 times 4 over n. I'll put the I after it, 4 over n I squared plus 2. This is all multiplied by delta x, which is 4 over n. If you square this, you get I squared, 16, and n squared. And here you can multiply this 4 over n to both terms of the parentheses. This is the limit as n goes to infinity of the sum of I going from 1 to n. Okay, so let's see. That's 2 times 16 over n squared times I squared plus 2, still times 4 over n. And in my next step, I'm going to take this thing and multiply it here and here. I'll put this on a new slide. All right, so we have the limit as n goes to infinity of the sum of I going from 1 to n of, that was 2, times 16 over n squared times I squared plus 2. and we're multiplying 4 over n like this. Okay, if we multiply that in, this is the limit as n goes to infinity of the sum of I going from 1 to n of. Okay, if we first multiply this thing here, we're going to have 4 times 2, which is 8, times 16, and that's equal to 128. Okay, then we get I squared over n cubed, because we have an n to the first times n. This then gets multiplied here, so this is going to be plus 8 over n. We can break this up into two separate sums, and we can factor out anything that does not depend on I. So this becomes the limit as n goes to infinity of, that's really 128 over n cubed times the sum of I squared going from, that was supposed to be an I, going from 1 to n, plus 8 over n times the sum of I going from 1 to n of 1. So what happened here is I had a sum, so I split it up into two separate sums. And then for each of those sums, anything that did not have an I on it, I factored out. So I took out the 128 over n cubed. Here I took out everything, 8 and n, and the number 1 is left over. The reason for doing this is on the previous slide, there's a formula for this. There's also a formula for this. I'm simply going to replace them. So this becomes the limit as n goes to infinity of, this is 128 over n cubed, and if you sum I squared from 1 to n, that's equal to n times n plus 1 times 2n plus 1 all over 6. For 8 over n, the sum of I going from 1 to n of 1 is simply n. This is great because in the second fraction, this cancels with that. That last piece is just 8. It does not even depend on n, so the limit as n goes to infinity of this thing is just the number 8. Over here, I'm going to rewrite this expression. I'm going to do this on the next slide. So we have this expression here. The 8 is perfect. Nothing happens to this as n goes to infinity. Over here, I'm going to swap the 6 and the n cubed. So I'll do that next. This is the limit as n goes to infinity of, that's 128 over 6, and we have n times n plus 1 over 2n plus 1, all divided by n cubed. The reason I'm doing this is I can write this as 3 separate fractions since I have an n cubed in the denominator. This is n divided by n, n plus 1 divided by n, and 2n plus 1 divided by n. So this is the limit as n goes to infinity of, that's 128 over 6, n over n, multiplied by n plus 1 over n, multiplied by 2n plus 1 over n, all plus 8. This is set up in a way so I know what the limit of each piece as n goes to infinity approaches. N over n, this has a limit itself of 1 because it's the ratio of the numbers in front of the n's. Same thing is true for this next fraction. It also approaches 1. Again, the ratio of the numbers in front of n are 1 over 1, or 1. This last fraction here goes to 2 because the ratio of the numbers in front of the n's is 2 and 1. If you evaluate this limit, it equals 128 over 6 times 1 times 1 times 2. Then we have plus 8. So that's multiplication. If we simplify this down to a single number, there's not a whole lot we can really do. I know 2 goes into 6 3 times, and 3 does not go into 128. This is 128 over 3 plus 8. So I'll put 128 over 3 plus 8. As a single fraction, this is 152 over 3, and that is the exact answer for the area under the curve represented by the definite integral.